Good afternoon. So in the last class, we introduced the Ito and Strashanovich integrals, and we worked out some simple examples of these integrals, which gave us a flavor for how the answer depends on these definitions. In particular, we saw that the Ito integral, because by definition its mean always is 0, so therefore its answer usually differs from the usual Riemann integral of deterministic calculus. Right? On the other hand, we saw at least in one example that the Strashanovich integral gave us the same answer. Now today we are going to apply these ideas to SDs. In particular, we'll derive certain important rules which are crucial for when we want to actually use stochastic calculus to manipulate SDEs and to get answers, and also to connect SDEs to the Fokker-Planck equation. Okay, so we are going to begin with what are called Ito's. So we are focusing on Ito calculus first, and we're going to look at Ito's mnemonics. Okay, which are heuristic rules that can be used as a shorthand to derive results rather than each time progressing with the integral. Okay, so the first thing, really these rules express something we've already seen, right, which is the key reason that there are differences in Ito results compared to usual calculus is that dw, right, the Wiener increment, has an order of magnitude root dt. Right? And that's why dw square terms survive. That is what gives us the dependence on where we choose to evaluate the integrand, for example. So the first rule is basically that dw square behaves like dt, okay, where the equality, I will define what it means, right? And related to that is that dw to the 2 plus n, okay, let me call it m, is equal to 0 for any m greater than 0, okay? So m is some integer. And so basically dw square can be effectively replaced by dt is the first rule. And the second rule is that any higher power of dw vanishes, okay, in the SDs. Now we know that SDs really they're just a notation for an integral, right? So what this really means, which is what we are going to prove now, okay, is that, let me say it below, okay. So the first one is that the integral with respect to some function, non-anticipatory function, okay, right, that this is equal to in the mean square limit, right, the same as of n, right, so this thing is equal to, but again this equality means statistical, right, the mean square limit, this is the same as writing, okay, over some appropriate limits. And similarly, the second one means is 0, okay, for any m greater than 0. This means if I see such an integral, right, where I have dw square, this stochastic integral is equal to the following deterministic integral, okay, where s is like, if you want to make it clearer, where I have now some time t0 to t, let's say. Okay, so this stochastic integral, if I have dw squared, becomes this deterministic integral. Okay. And any integral with dw greater than power of 2 basically drops out and becomes 0. So how do we prove this? Remember, this equality means that the partial sum that defines this integral becomes that partial sum in the mean square limit, right, of the sum going to infinity. So that's what we're going to prove, okay. So what we want to look at is the difference of these two guys in the partial sum. Right, 1 to n. And now the difference of these two must be 0, right? So I can take the integral common and the g common. So I'll get g at, remember it's Ito calculus, right, multiplied by the difference of these two guys, right? So dw what do I call it, delta or d, Yeah, delta Wi, because now I'm discretized. Okay, minus delta Ti. Or delta Si since I used S. And this difference, variance, has to be 0. So it's the since I'm using S here, let me retain S. Okay, that is just the integration variable. Okay. So is this clear why I wrote this? So this has to become 0, okay, for this result to hold. So I just took the difference of the two, right, in the partial sum. So G becomes common, and then it's delta Wi square minus delta T, right? That whole difference, I want to take the variance, right? So square and then ensemble average. Okay. Fine. Now we'll do what we've been doing in the past derivations. It's the same idea, right? So you take the square inside and expand. So this is equal to now, okay, let's take the square in. So you'll have summation, I write this as gi minus 1 square, right, times I to the 4 okay. Okay, so I just took the square in, and now we have this sum, right? And I have to take the ensemble average. Okay, so now when I take the ensemble average inside, remember that gi is evaluated at the beginning of the interval. It's a non-anticipatory function, so it's uncorrelated with all this stuff. Okay, so the ensemble average will split. And when I take average, what will this become? Delta S square. So remember, S is like time, right? So we already know that this term will become 3 times delta Wi square, the whole square. That means this will be 3 delta S square. Okay, this is already delta S square, right? And this thing will become delta S square again, because this will be like delta S. Right? So this is delta S square. This is also delta S square. Yes. Yeah. That is here, right? No, the other term. That is the, so 2 has to be here, sorry. Okay. So coming back, you can see that what we had done in the last class, right? Because this is a Gaussian, so the fourth moment is 3 times the second moment squared, and second moment is delta S, right? So 3 delta S square. So this goes like delta S square, this goes like delta S square. Here, this will give me a delta S times delta S square. So this entire thing is delta S square, right? Which we know goes like 1 over n square. So all of this will go like 1 over n square. Now if we come here, again the mean comes into each component part separately. Okay? If I multiply these two, you will see the only thing that survives is going to be the product of the delta W's. So that will again go like delta S square and delta S square. Any cross products will vanish. So in the end, I'm going to get this thing also going like 1 by n square. So then as s goes to infinity, I'll get 0. The operations, I'm going through it quickly because they are the same as what we did in the last class. Fine, so what we have shown here is that the mean square limit of the integral, right, the stochastic integral with respect to the dw square, right, this thing converges to the deterministic integral of g into dt, which is basically what the first mnemonic says, that whenever you see dw square, you can just replace it by dt. Okay, which is a formal way of basically stating the idea that we saw in the last class, that every time we see dw, it behaves like root dt, and therefore we have to retain terms up to dw square. This is just proving it when it appears in any general integral. That's why it's multiplied by g. Okay. Otherwise, by itself, of course, we know that the variance of the Wiener increment is d delta t, right? That is directly given by the Wiener process. What we are showing here is when it appears in a stochastic integral multiplied by some arbitrary non-anticipatory function g, right, we still have the same behavior, right, in the sense that the integral with respect to dw square becomes a deterministic integral with dt. Now the question is, what happens if there are higher powers of dw? Okay, so here the statement is that we can already anticipate it, right, that if I'm going to retain terms up to order dt, which is what usually happens in integrals, right? So this dw survives because it behaves like dt. And that's exactly what we're saying, right? Any difference between them is of higher order and vanishes. So here my integral is already starting with a higher order Wiener increment, it should vanish. So if we try to follow the same idea, I'll want to show again that this variance goes to 0 except there's nothing on the other side. So to prove the second thing, right, of the second mnemonic, all I need to show is that the partial sum again to the power now 2 plus m right. I want to look at this, right, and this thing should vanish to 0, okay, because there is no right hand side. So it's just the variance of this partial sum itself. So once again, I have the same kind of expansion. Yes? Ah, sorry, just one. Thanks. Okay, so it's the same thing. Now, it's pretty easy to see that this will vanish, okay, because once again, I just have to look at how the delta W's become delta T's or delta S, right? So it depends on m, right? If m is such that any power of delta Wi is odd, what will happen? That here I had only even power, only squares, right, which I replace by delta S here or delta T. Now in this case, we know that delta Wi to some odd power is what? What is the odd moment of the Wiener increment? Remember, the Wiener increment is Gaussian. So the odd moment of Gaussian will be 0, right? So I know that that is going to be 0. So for any m such that I get an odd power, it will, the ensemble, when I take it, will go to 0, right? And any other m which is even, right, will be because I'm taking 2 plus m, this will also go like, will be smaller right? And so it will also go to 0. Okay, because it's always 2 plus, right? So it's some higher power than delta t, because I proved it for here, right, without the m. So now I'm taking a higher power, so those even ones will go off, sorry, and the odd ones will anyway vanish. Right? And therefore, I'll be able to show that this whole thing goes to 0, which then proves the second rule, that whenever you see dw to some power greater than 2, whether it's even or odd, you can just drop off that term. Okay, that integral will vanish. Yes. Thanks. Okay, so we had done exactly these operations in the last class for specific integrals, right? And we saw similar things happening. So this just kind of gives us a quick shorthand, so that whenever you have to prove some result, you don't have to start with the integral and then look at the partial sum. Right? You'll always have exactly the same thing working on. So then for quick calculations and for deriving the subsequent formulas that we're going to do in today's class, we can directly use these rules. And they're written in this form because you can directly apply them to SDs. With the thing at the back of your mind that if suppose you see a term, some function dw square appearing in an SD, in your mind you know it's really integral of that integrand dw square, and I can replace that integral with the deterministic integral, and therefore in the SD I can directly replace this with dt. Okay, this is the logic. Fine, so with these rules now, you will see that actually working with Ito SDs is not difficult, and we can figure out how they transform, how they behave, etc. Just like we would manipulate normal ordinary differential equations, we can do similar things, but we have to keep this thing in mind. Okay. All right, so let us now apply these rules to see how Ito calculus is different from usual calculus. Right, again, we're looking at the Ito version. So now what is the idea? Let's say I have a function. Okay, I have specified some function of time and of the Wiener process. So it's a stochastic. The function f will be stochastic because of its dependence on Wiener trajectories. Okay, so as I generate one Wiener trajectory, let's say this function is like sine t cos w. Right? I generate one Wiener trajectory, so w is fluctuating in time. I can evaluate sine t cos of the Wiener process. I'll get some other fluctuating trajectory. Right? And what I would like to know is, if I make an increment in time dt, right, which will have this corresponding increment dw, what will be the increment in f? Okay. So what is df, right, for dt and dw? So this is what we would do in calculus, right? If it was normally deterministic, I would take the derivative of f. Or I'd use a Taylor series. So this is the equivalent of, what is the equivalent of the Taylor series? We've already seen that the Taylor series result has to be extended because of the Wiener increment behaving like root dt, right? So now we will derive the same thing. So I would say the increment df, right? So remember, this is just some explicit function. I can always take its derivative. Right? Plus, but now I should not stop, because the mnemotechnical rule tells me that I will have a dw square which will be of the same order. Okay, so if I want to retain up to the leading order, I need to take another term, right? Otherwise, because I'm retaining this guy. So I will have 1 by 2 now dw square. And then the higher order terms, if I write out, will give me dw dt, dw cube, and all those will drop out. Okay, so what I didn't say up actually was extending that. If you have dw dt, that also drops out. Okay, because the basic idea, okay, so let me write it now again. Use Ito mnemonics. Okay, and the basic idea is that dw goes like root dt, and we retain only order of dt terms. Okay, so that means if I have dw square, this is like dt. Okay, dw is left as dw because it's stochastic, but dw square becomes deterministic. Okay, if I have dw dt, right, this should go like in this logic, right, to 3 by 2, which is greater than dt, so this I'll drop off. Similarly, dw to any other higher power like 3, dw4, etc., all of these drop off. Okay, this is the logic. So therefore, you can see if I extend the Taylor series, I'll get dw dt, dw square, cube, etc., and all those will drop out. Dt square from this deterministic part, that will also drop out. So this is the end of my equivalent Taylor series. Okay, and when I replace the mnemotechnical rule, right, what I will get then after using, right, the mnemonic, I'll get df, right. So the equivalent transformation or Taylor series is df dt plus I get a contribution from the dependence on the Wiener process, okay, which is new. Okay, so this is the equivalent of Taylor series in Ito's calculus. You have that extra term, right, from the second order dependence of the function on the Wiener process. That's the exact same thing we saw appearing, right, when we tried to look at the mean value of a stochastic integral depending on where it is evaluated. When we did the Taylor series, we realized we had to retain this term because in the partial sum, delta w square term survived as dt. Now, we are just using the Ito mnemonic gives a shorthand to proving the same thing we had done earlier. Okay, so that's fine. This I showed by illustration, but what's going to be useful for us is to consider this same question in the context of SDs. Okay, so let's do that. It's going to be very similar. So now let us, right, begin by considering an SD, okay, for the evolution of some variable x. So we start with this SD, right, a dt plus b dx. Okay, it's an Ito SD. Right? So whenever it's Ito, I don't put that big circle. If it's Stratonovich, I'll put the circle. Fine. So this is an Ito SD, right? Like some version of the Brownian motion, but with some drift. And b can be some function of x. Right? Sorry, what did I do? Okay. Right. So this is a standard SD. And now I ask the same question. Right? I want to transform, in other words, right? So I want to find the SD for some other function. But that is why I said transform, because this is what we do when we do variable transformation. Right? If I have an ordinary differential equation for x, and then I want to define a new function like y is equal to sine x, and I transform the equation dx dt to dy dt. Okay, so I do that by saying y is equal to sine x, and I differentiate y, and I substitute dx dt, I get an equation for y. That's how we transform equations from one variable to another. Right, so similar transformation of variables basically involves, if I know the equation for dx, can I find the equation for df? It's a standard thing. For example, this is what we would do if we want to change coordinates. Right? So if I have a pendulum, I can calculate the pendulum's motion in terms of its x and y. Right? If I have two variables, velocity and position. So let's say x is position, v is velocity, I can get its dynamics. Right? Or I can switch to polar coordinates and do things in terms of amplitude and angle and its velocity. So polar coordinates. So there I would have to transform, right? I would say R is, rather X is R cos theta, that kind of thing. So it's the same idea here, right? But you will see this now brings in something new and interesting. So we use the same concept, right, as we did there. So to find an equation for f means I want to have df is equal to something dt plus something dw. So let's use now the new version of the Taylor series. I can either just apply this or let me just do the usual expansion, but keep in mind Ito's mnemonic, okay? So df again, I'll have dou f by dou t dt, that comes from the explicit part. But now I'll have dou f by dou x dx, and let me go to higher order, anticipating that I may need dw square terms, okay, which will not come from here, correct? Because I'm going to substitute dx here, I'll only get dw. Okay, and now you can go ahead and substitute. So this term will give me dou f by dou x times a dt and what will this term give me? Okay, so dx square, it will give me a dt square, that will immediately drop out, right? And b dw square, which will behave like dt, right? So I'll get b dt. Sorry, I had dx square, right? So it should be b square. Okay, so this result is crucial. Okay, this is what we're going to use again, right? And maybe the most important result. Right? This thing is called Ito's formula. Right? It's basically a transformation formula. So if I have an SDE for x and I want to find the transformed SDE using a transformation involving a function f of x comma t, then you have to use this rule, okay, which differs from the usual calculus rule by this second order term. Okay, so otherwise you will have the same kind of behavior, right, if it was a usual deterministic thing, but the difference comes from the dw square term, right, which is this second order term. But actually it becomes first order simply because dw square is dt. So if you like now, if you look at this equation, right, I started with this, it has a drift and it has a stochastic part, okay. Now, when I transform the equation, you see what's interesting is this, I have an extra drift, right, and that extra drift is coming from the stochastic part. That is the funny thing. So of course, when you transform what was earlier the drift A will become something else because you are looking at a different function. That's not surprising, right? But what is important is you look at the components of the drift, right? One part of the drift comes from the explicit dependence of f on time. Okay, that's fine. If you want to simplify it, forget about f depending explicitly on time. It's just some transformation of x. So instead of looking at x, you look at x square, you look at sine x or some other property of what you want to measure. Right? Now, what is interesting is when you do that, it's not surprising that the drift will change. It will change exactly like A df by dx. So in other words, this part of the drift is coming from the original source of the drift. It's just that because you're looking at a different quantity, some other property of x, like x square, for example, that will change. What is intriguing now is, in addition to this, the Brownian fluctuating part is also giving you a deterministic drift. Okay? But only if, yeah, it's also giving you a deterministic drift because of the B. Of course, F should have some second order dependence on X. If it's linear, it won't. But already that is a surprising thing. Right? That's the important thing about the rule. Yes?
Which means something that is meant to be stochastic and therefore random in all directions would still end up creating a directional bias.
Yeah, depending on what you look at. No? But you already know this, because Brownian motion gives you zero mean for the position. But if you look at the position squared, which is the displacement, of course you will not have zero mean. So you already knew, right, that if I have a stochastic noise, even if it's additive, so even if B is a constant, right, and it's adding plus minus to the basic native quantity, if you like, is just the position, right? So I'm taking step forward, step back, and so on. My mean position is zero, because it's just additive, unbiased Brownian walk. But if I look at displacement square, if I look at displacement, that means I have to square my position and then take square root, or even if you don't take square root, then mean square displacement. Right? Immediately I will not get zero as the mean, right? I will grow like t. So that is what this is showing you in general. That's so if, for example, if you apply x square to this, you will get exactly dt, right? You will get the drift. So if A is 0 in the Brownian walk, right? A is 0, B is 1. Okay. Fine. So A is 0, this will drop out. Right? I am going to look at a transformation instead of x. Let me look at x square. So x square has no dependence on time. This will drop out. No velocity. This will drop out. What will survive is 1 by 2 times the second derivative with x, right, which is 1. So this 2 will cancel. I'll just get 1. So it will go like dt. So the drift equation for x square, so d of x square is just dt. Right? And then you have the Brownian fluctuation. So then if I take the mean displacement, that dw will drop off. I'll just get the mean of the change of x square is dt. Yes.
So that double partial derivative basically covers coverage in x square, basically the variance type of b square.
Locally, yes. I don't know what you mean by variance. It's just some function, right? So I choose some transformation which is not linear. That transform variable will have a drift from the Brownian motion. Yeah, so if you like, you take some other function like cos x, but then locally to x, the quadratic part of that cos is coming from mean square displacement, if you want to think of it that way. But then the fact that if it's cos x, then the second derivative changes with x, that will like modulate the diffusion. So an immediate application of this is if I come back here and I say this is an E to SD, right? So the mean will just be A dt, right? Because the mean of this is always 0. B is uncorrelated with dw, okay, in the E to SD. So if I take mean dx, if I apply the mean will only be the deterministic part, that will drop out. But if I look at the SDE for some nonlinear transformation of x, right, that mean will have a contribution from the Brownian fluctuation. Okay, so that will not drop out. And this is an important insight, because when we do stochastic modeling, why are we adding the noise? Right? In the end, we typically don't want to look at individual trajectories, because those individual trajectories contain arbitrary noise for which we have no real information. Right? We have replaced some uncertainty with the noise. So it's not any individual trajectory that's really of interest. Usually we want to look at statistics. Right? And then we added noise into our models to give us the variance, the fluctuation, right? But again, in a statistical sense. So if always taking averages would drop out the noise, there's no point putting it. But the reason we do it is precisely because of this, right? So the native basic quantity, you add noise, you take the mean, the noise will go off. But any moment of that quantity, which basically looks at the mean of some nonlinear transformation of the quantity, right? Like x square, x cube, those will give me the moments. Those things will have non-zero contribution from the noise you added. So therefore, when you develop a stochastic model, adding the noise gives you useful information for the higher order statistics, which is actually what you want, right? The mean, if there is no bias, the mean will not be changed by addition of white noise. Right? I'm talking about white noise now. It will not, right, change. What is interesting is the variance, the moment, and so on. So for example, if you think of chemical reactions, right, or population dynamics like Lotka-Volterra or some other models of population growth, you can write down deterministic equations which you can interpret as the mean. So directly you can have exponential growth of, for example, cells, you can have exponential growing model, you can have Lotka-Volterra which gives you cyclic behavior. These are classic deterministic ODE models. So now you can always say, okay, but in reality there will be fluctuations, I will never see a perfect, right? So if I look at number of some population with time and I have some exponential growth predicted by a deterministic model, I can do a SDE type model where I put some noise, right? And that will give me some result like this. Right? So what is the point of doing this? Right? It's nice to create some trajectory, but if I'm just looking at the mean, the trajectory will collapse back to the exponential. So I can say, okay, I'll just do the deterministic model. Right? So is the point of studying the stochastic model just for decoration, that I can show there is a fluctuation? That is not true, right? What I'm doing the stochastic model because then I can get the cloud. Right? And because it's exponentially diverging, you would expect small initial variations will also diverge. Right? If the model is not exponential, the cloud of errors will behave differently and so on. So you want to calculate that cloud because that will give me how, if I know the population now with some uncertainty, that after 100 years, how will that variance grow? And this is important for policy decisions and whatever. Right? So it's precisely to calculate the moments, right? And those moments are nonlinear transformations of my basic variables. And they will have drift contributions, have mean effects of the fluctuations. Okay, so this is why this immediately tells you that it makes sense to study SDEs, even if we want to have the mean statistics, as long, of course, of higher order moments. Okay, and the most simple example is mean square displacement with Brownian noise, okay, where the mean x will go to 0 in the absence of any a, right? But x square will not have a 0 mean, it will grow like dt, grow like time. This also tells you that if I had d of x square, which is nothing but telling me how x square of any trajectory will vary, that will of course have a fluctuating part. But if I calculate all the x squares and average, the fluctuations will vanish. This is exactly what you have already done in your first assignment, right? You got trajectories x, you squared them. Right? Now you didn't plot the squares, but if you had plotted x squares, you would have also got fluctuating things. It's only when you took the averages and you took n large enough, it collapsed to a nice line. Right? That line is basically this stuff only. Okay. So we now see what we could not do in the original first class, right, when we looked at Langerhans equation. Remember, if you go back to that derivation, right, we started with an SD, but written in that heuristic ODE style. And then we did some derivation and we got that the mean x square goes like t with a diffusion coefficient. That was what we did. Right? But to do that derivation, we didn't use a mathematical solution because we didn't know how to solve the ODE. Rather, we did some manipulation. We introduced a kinetic energy. We used statistical mechanics, equipartition, and then we got our result. Right? So if you remember, I told you at that time, to go back to the lecture, looks like we did some magic trick and we got the answer. Right? Now we know how we can derive that properly, right? Because we can start with Langevin model, which I would now not write the way he had written there. I will not write d square x dt square equal to it. I'd rather write it for an increment. In the dissipative version, I would just write, right, dx is equal to this fluctuating part. And then you would do exactly this. You would use Ito's formula and say, if I want to find how the mean square displacement varies, dx square, I use Ito's formula where f is equal to x square. I'll get a new SD. Then I take the mean. And when I take the mean, the stochastic part will drop out. And I get only the deterministic result I want, which will tell me that x square goes like t. And the diffusion coefficient will be b square. Okay. That means if in Einstein's derivation d was the diffusion coefficient, right, here b should be root d. Okay, we'll get this again more clearly later. So this is the value of Ito's formula, right? I can now, with this understanding of Ito's calculus, rewrite Langevin equation as a proper SD, and then simply from that SD transform to an SD for x square. Right? I'll get another SD. Then if I take that mean, I'll directly get mean square displacement result, okay, without having to introduce any appeal to statistical mechanics. Okay, fine. Any questions about this? Okay, so that's why it's a fundamental basic rule, right? So if I start with the SD, I can analytically derive the equations for all the moments. Okay, and if the problem is simple enough, I can directly solve that. I can directly get the result. I don't even have to do a computation. Okay, so what you did numerically in the first assignment, we can show analytically now. Okay, suppose, so far everything we have done has been for a scalar variable. Okay, but I'll just state the result in vectorial form because that will help me later. So suppose I had an SD to the vector form. Okay. Okay, so I'll use Einstein notation. So I'll have dxi. So xi is a variable of x1, x2, x3. They're all stochastic variables. Each of them have a corresponding SD. Okay? And in vector form, I would write it like this. So this is the whole vector. This is equal to some vector of velocities dt, right? And now each of these processes, x1, x2, x3, will be driven by some Wiener increment noise. So definitely I'll have dw here, okay, j, because those will have a coefficient, and in general, I could multiply each of these. So this is another vector, right? I can multiply each noise with some number. That would be like multiplying it with a diagonal matrix. Or I could say that x1 is driven by dw1, dw3, and whatever. So I can recombine this vector and drive each of them, right? So in general, I can put a matrix here. So that B becomes a matrix, okay? So if Bij is diagonal, it would be like saying, okay, each Wiener increment only drives the corresponding X process, right? But I can, of course, combine the Wiener increments in some way. So an example we'll be looking at later is a polymer molecule. Right? So we were doing Brownian motion, you just have one particle. I just have x1, and there's only one noise acting on it, the Wiener process W1. Okay, now suppose I take two particles and join them somehow. Right? It's a simple model for like a filament. So I take two beads and I join them. Okay. Now I have two beads, I can have two Brownian noises. So W1, W2 acting on position x1 and x2. But now x1, of course, will get affected not only by its Brownian noise, but also the Brownian noise on the other bead, right? Because it's connected by some spring or some line segment, right? So then each bead is affected by noise on both the beads. So you will see that dw1 and dw2 will affect x1 and vice versa. So I should have some matrix that combines all the Brownian fluctuations being experienced and puts it on each variable. Okay, so this is a general, completely general way of writing a vector of SDs. Okay. Now, of course, you can do more complicated things here, but this is anyway deterministic, so it doesn't matter, right? The main thing is this. Okay, so now when I apply Ito's rule, I would do exactly what I did before. I want to look for df, right? Where now f is a function of the xi's and the dw, right, j's, okay, of x bar and the Wiener processes. I can, of course, have a whole bunch of functions, but then I'll just repeat the formula for those functions. So I'm writing it only for one function. Okay. So an example would be like the energy in the system. So I have many different variables, and I can define the energy as, in some way, some functional of all the things. And then, right, I want to know how the energy changes as all the particles in the system are evolving, for example. Okay, so then I would do a Taylor series, but now multi-dimensional Taylor series, correct? And yeah, I would have to take dou f by dou xi dxi. Right? Similarly, dou f by dou wj dwj and so on, okay, and then substitute. The important thing is what will happen when I take this thing square, right? So the square should be dxi dxj, and then I will have a product of these things. Okay. So anyway, you can do the derivation at home. It's pretty straightforward. I'll just write the final answer now. Okay, so there's a drift part which has, that is the analog of what we did before. So you can look at that. Right? So I'm not making f a function of time. Okay, that you can always add if you want. Okay, so when I do the Taylor series, I would have, right, dou f by dou xi dxi, which will bring in the ai. Okay. And then I'll have the corresponding term here also. Let me put that here. Right, so when I do Taylor series, I'll have dou f by dou xi dxi. That will give me an ai dt. Right. The other part of dxi will give me a bij dwj. Now, when I come to the second order term, right, I'll have half dou square f by dou xi dou xj times dxi dxj. Okay. So when I do dxi, I cannot use this j, right? I should use like k over there. And then similarly, I'll have to write, instead of I put j, and then k, and then I do it. Right? Then I take the product. So therefore, then you will get bik bjk. Right, where we should note now that because this is a matrix, right, bik bjk is the matrix B transpose. Okay. Because a normal matrix multiplication B into B would be bik bkj. Right, that is the definition of matrix multiplication. The swap means I am multiplying it with its transpose. So if you remember matrix multiplication, right, it is row times column. So normal matrix, if I was just doing B into B, it would be bik bkj. Because I flipped it, it's bb transpose. And this makes sense because this is then positive definite. It's like b squared. Okay, and it's the analog of the scalar version which has b squared. And that should be positive because that is like some kind of diffusion, right, which we can already anticipate from when I said we look at x square. So if I were to do the same thing here and say this is a multi-dimensional, some kind of Brownian walk, and I look at dxi dot dxi, that this will become like some kind of diffusion. Okay, so anyway, this is just a simple multi-dimensional extension of Ito's rule. We will use it later when I just introduce multi-dimensional version of some results, but the derivation is basically the same. It's just doing Einstein notation carefully. So there's no new physics in that. Okay, so if this is okay, let us now do the exciting thing of looking at the Stratonovich case, which will finally show us why the Stratonovich definition is of interest. Okay, so let's now look at the Stashnovich SD. Okay, suppose I start with that. Okay, I now have the big circle there because I'm saying it is Stashnovich. Okay, this means what I'm really writing is x of t is equal to x at 0 plus integral a dt plus integral b to dw, where that integral is defined in the Stashnovich sense, which means the b is not evaluated at I minus 1 in the partial sum, but at the midpoint. Okay. So remember, I want to now use the mnemonics where I do with the differentials. So this is like saying that, right, plus b now, so b is generally a function of x, right? That is when it will become interesting. Right? Otherwise, there's no difference. Right? If it's not a function of x, remember the where you apply doesn't matter. If it's a constant, that question doesn't arise. So when it is a function of x now, I want to do it at x I and this is basically what I'm doing. Right? Or in other words, and what I want to do is, given this, right, I want to find df again, where, right, f is some function of x. Okay, so again, the time is deterministic, doesn't matter. That will behave the same way. Right? But if I take some function of x now, like I want to find x square, right, just like I did with E2, what would be the corresponding equation for df, but the Stashnovich equation? Okay, that means I want to find some equation for df where the noise part will again be evaluated at the midpoint. Okay, so the question is how to do this. No, I'm not doing the t. That's anyway deterministic, it will do the same thing. It will just be df dt dt. So forget about that. Okay, the interesting part only comes from the dependence on the stochastic process. Okay, so now this is where we will go back to what I had indicated a few classes ago, right, which is that like Euler's bit point rule derivation. So what I want to do is, using a Taylor series on f, get some equation for df, but which has a form where I evaluate b at the midpoint. Okay. So what we will do is we will expand f, right, at xi minus 1 and at xi about its midpoint. So we do a Taylor series, right? So again, in Ito's case also we use a Taylor series, but we used Ito's mnemonic, right? Here we don't have that mnemonic because we are thinking of looking at I mean, at least at this point, this is a Stashnovich equation. Okay. So I cannot directly apply that. I cannot apply Ito's mnemonic to Stashnovich, right? Because my derivations of the mnemonics were all for Ito case where there was no correlation between B and DW. But now that I'm evaluating B at the halfway step, that means the value of B involves the dx, and that dx obviously depends on the dw. Okay, so if I try to do the derivation will collapse. If I take the average, it will remain as average of this quantity because these things are correlated. Okay, so what we will do now is, let us write f of xi about the midpoint, xi minus 1, let us start. Okay, so I need to step forward. So I'm going to, MP just means at the midpoint. That means at xi plus dx by 2, right? And I go to the higher order. Okay. And similarly, I can expand it, right, at I, which is forward, right, which is again MP is midpoint. That means I'm evaluating it at xi minus 1 plus dx by 2. sorry, it's the other way around, right? So I'm taking the midpoint and I'm going backward here. So I need to put, so this is minus, right? And this is plus, right? So this is ahead. So I take the value at the midpoint and then I add dx by 2 times the derivative, okay? And here I'm stepping backward from the midpoint. So it's minus dx by 2, right? Times the derivative, times the slope. But now when I go to the second thing, it's anyway the dx squared, right? So the minus doesn't come in. Okay. But now if I do right 2 minus 1, right, what will I get? I'll get df is equal to okay, so you see what has happened now? This is exactly the step, if you remember your numerical methods, this is the kind of trick we do to get Euler's midpoint formula to become second order accurate, right? Because the second order term errors vanish. So then the errors that are left are higher order. Now when we do the same thing and you take the difference, right, you get f at xi minus f at xi minus 1, which is df. Right? The only thing that survives is the first order term, the second order term vanishes. Okay? And so I get exactly, right, I mean, up to dx square, right? And higher order terms you can anyway show will drop out. Right? So then we have df is equal to df by dx at the midpoint times dx. This dx I substitute back the Stachanovich equation, okay, which I can do. And now I'll get this at the midpoint and b into df by dx, the whole thing evaluated at the midpoint. Okay, so I change the diffusion term in front of the dw, right? I change the coefficient of the noise, but it's still evaluated at the midpoint. And this thing being evaluated at the midpoint or not does not matter because this is a deterministic integral, right? So here, where I evaluate this in the small interval has no effect, right? The corrections are dt square as we had shown. So this becomes as, it doesn't matter anyway, it looks like a usual thing. So then I'll finally can rewrite this as a, right, dou f by dou x dt, and this, because it's at the midpoint, is by definition now a Stachanovich SD. Okay, so I've got the new Stachanovich SD for f from the Stachanovich SD for x, and you see now the transformation rule is the usual calculus rule. Right, so if I didn't know anything about SDs and I treated this as some normal kind of difference equation, right, then I would just do usual calculus, retain the first order term, throw away the higher order term, I'll get exactly this. Okay, so this is what I was hinting at earlier. The main difference in stochastic calculus is because of the behavior of this Wiener increment, which goes like root dt, right? So that's why you always have to keep the higher order terms because you're keeping things in the integral accurate up to dt, right? So dw square has to be retained, right, typically. But you can see here the second order term, which would have given us that, gets cancelled because we evaluate things at the midpoint. Okay. And so because of this, the Stachanovich definition is the only definition where the usual calculus rules apply in 1D. Right? Whereas other definitions, you will not have the usual calculus, right? And the problem is you don't know what would apply, right? It becomes complicated. Right? The only case which is simple to find what the new rule is the Ito case, which we had done first. Right? So therefore, these are the two critical definitions. The Ito one, which is simple and allows us to derive the new calculus rules, right? In particular, Ito's formula using Ito's mnemonics, and then we can do various other derivations with that. So Ito is what we need to work things out mathematically. The Stratonovich case is important because it obeys the usual rule of calculus. Okay. Now, why is that important? So this brings us to the whole point of what we are doing, right, which is to model physical systems. Right? And if your stochastic model is really a model for an actual physical process where there is no such thing as delta correlation. So take the random walk problem, for example. You have some particle, it's experiencing a noise. What you're saying when you replace the noise, when you're using a Wiener process, is that I'm looking at the phenomena on large enough time scales so that whenever I experience the noise, it is uncorrelated with the previous noise I experienced, no matter how much I resolve my model, because I'm still operating at much larger time scales than the molecular phenomena. But if you zoom in, of course, things are correlated, right? Nothing is uncorrelated at some fine enough temporal scale. Okay. Now, in the case of turbulent flows, that's even more obvious, right? Because what we do is if we look at large scale, long time behavior, the turbulence will look like it's random and fluctuating and give us like diffusion, some kind of diffusive behavior that we model with eddy diffusion. But if you, of course, zoom in, you know that it's satisfying Navier-Stokes equations, everything is correlated, right? The way a fluid parcel moves is completely dependent on where it was before, right? It is actually a solution of the Navier-Stokes. So when you try to develop stochastic models for turbulence, it's very obvious that it's only uncorrelated on some large time scale as an approximation, right? But actually you are modeling some correlated physical process. It's just that the correlation time is very, very small. Okay, so if you take this approach and say my SDE is the limit of actual physical process where that forcing function is very noisy and the correlation time of the forcing function vanishes to 0, right? It goes very small, right? That limit is my SDE model. Okay, then what you should expect is that whenever, if you take a finite correlation time for your usual model, right, for the physical process, that should satisfy normal calculus. Right? It's only when you go to the limit, and therefore the limit that you get, you also want that to satisfy normal calculus. Right? Otherwise, it's strange. Then you will have a disconnect, right? Because your physical model, which you, let's say you write an ODE, normal ordinary differential equation, and you put some right-hand side, which is some sinusoidal forcing of very high frequency. Or you can add many different sinusoids, make up some noisy signal, right, and take that frequency to very large values. That will start approaching some very rapidly fluctuating signal that starts looking like white noise. So if you do this operation at any finite correlation time of the fluctuating signal, normal calculus will apply because it's just an ODE. It's only when I take the white noise limit and I get the Wiener process, right, that breaks, and then I get all these different possibilities for the definition and so on. Right, so if I view my model as some limit, right, of a physical process, I should want my model to obey the usual transformation rules. Because for any, however small, finite correlation time, I'll have a normal ODE which will transform in the normal way. Okay, so this is just a heuristic way for arguing it. There are certain theorems that have been proved, which I'll discuss later. Okay. But based on this heuristic, suppose I was looking at, again, the variation of some population, right? And I write down an ODE for it and I add some noise. And now because I don't know what noise to put, I take the white noise limit. Okay. But the SDE I write, I will want that SDE to be Stratonovich. Because only then, if instead of looking at the population, I look at the square of the population, right? Or instead of looking at some particle configuration, I look at the energy of the system, and I get the equation for that energy, right? For the transform variable. If I do it to a normal ODE with some forcing function which you prescribe, it will transform in the Stratonovich way. Okay. So if I don't do Stratonovich, it will be weird, because then it's like saying any small correlation, no matter how I take some, right? I can always cook up some signal by adding a bunch of sinusoids of very high frequency. This will be something noisy. And if this thing is super small and I look at phenomena at very long time scales, this is as good as becoming delta correlated, right? Anyway, my simulations are only going to approximate it. So I should want this to behave like this is a normal ODE, it will transform like this. right? So it's a weird thing to say for any finite thing, it's transforming like that. But if it's 0, I'm going to transform it in a different way. Okay, so just on this heuristic idea, when you model physical systems, right, and you replace some fluctuating process with the Wiener process, we will put in Stratonovich because that will give us the same calculus rules. Okay, but when it comes to numerically simulating or deriving analytical results, we can't do that with Stratonovich. Okay, then I need to come to Ito. Because remember, only in the Ito case, I have the Ito mnemonic. I can directly derive results for f and so on. Okay. So for example, let's say I have this equation for x. Okay. I can get the Stratonovich version for x square. But I don't know how to solve this because if I take the average, right, this will be fine. But what is the average of this? I don't know. Right? Because the average of this is the average of these two correlated quantities. It doesn't go to 0. It is something finite. I don't know what it is unless I actually solve. And there's no way for me to solve it analytically. The difference in the Ito case is if I have an Ito equation, remember, right, I get this equation now, where if I take the average of this SD, this fluctuating part drops off. And I have analytically the result for how the average varies. Okay, that's why Ito is powerful. So if I have an Ito SD, I can transform it to whatever quantity I want, and I can get the average of it directly because the stochastic part will drop off. Okay, but the Ito SD does not correspond to physical processes. Right? The physical process will transform like Stratonovich, so I have to model it with Stratonovich. Right? So here I can get dx square. The problem is that this average is not 0. It should not be, right? Otherwise, it will tell me if there is no velocity, it will tell me that mean square displacement is 0, which it is not. So it is precisely the correlation between the Wiener increment and the diffusion at that half step that is going to give me my mean square displacement. But I cannot obtain that analytically here. Okay, so what we need to do is some way to, if I look at a physical problem, I replace the fluctuating part which I don't know with a Wiener process, and I interpret it in the Stratonovich way. That's how I will start my modeling. But to get any useful results, right, I need to transform somehow from the Stratonovich to the Ito SD. And if I can do that, then I can do Ito's rule, I can use Ito's mnemonics, I can do simulations, etc. Okay. So what we are left to do now in our program is to find a way to transform from Stratonovich to Ito. If we do that, then we are fine because we can begin modeling with Stratonovich, right? Because it satisfies the same rules of calculus. And then I can transform Stratonovich to Ito because with Ito I can develop numerical schemes, I can prove analytical results, I can ultimately derive the corresponding Fokker-Planck equation only for Ito. Okay, so this is what we're going to do in the next class. I think we can take it up, right? Because you will see that it has to do again with the treatment of this, right? So B is evaluated at the midpoint. If we can somehow replace this with B being evaluated at xi and account for that difference, then we will get an Ito equation. But how to do that is a little tricky. Okay, so that's what we look at in the next class. And then once we know how to transform Stratonovich to Ito, then we can just look at Ito problems and then use Ito calculus to connect SDEs to the Fokker-Planck. So we'll stop here. We'll take that up on the next class.